let's have a chat about differentiation. So what we're doing today is we're going to, I hope, work through everything that you cover in differentiation for AS Maths. The idea is to have a look at all the formulas and theories and concepts today, and then next week we will do some past paper questions to actually practice what we've covered today and give you more of an idea of what things look like when they come up in the exam. So this is very much a theory-based session. So if we go all the way back to the beginning, and we're understanding sort of why we use differentiation at AS, and it's all boiling down to those rather pesky gradients of curves. When we consider a curve, doesn't matter what shape it is, it can be all sorts of fun and funky things, okay? But the thing is that throughout that curve, the gradient changes. We might get one or two spots where the gradient is the same, but from one x value to the next x value, the gradient is changing. So this means that we can't have a single value to represent our gradient. If you think of a straight line, if you think of y equals mx plus c, m is our gradient, it never changes. When it comes to a curve, we can't have a single value. We can't have an m for gradient because it's always going to change. So how do we represent this? Well, we need to think about what does it depend on? And there's two really cool things, okay? The gradient is predictable because it depends on two things. It depends on the shape of the function. If we look at our little collection here, you can see that the gradient of each of these is different because the shape is different. But also where we are on that curve, okay, that is also going to affect what the value of the gradient is. The value of the gradient here is different to the value of the gradient here. So where we are on the curve is all about the value from our x-axis, which is the value of our independent variable. So if we can find some way to combine these two together, then we can actually now look at the gradient of our curve. And that is what differentiation comes in and does, is differentiation says, okay, so let's look at the function of our curve and relate that to the function of our gradient. So we are developing a function to understand our gradient, because then we can put in different values of that independent variable and understand what is the gradient at that point. At that value of the independent variable, this is what the gradient is. So we are developing a gradient function. We need some new terminology to go alongside this. Okay, and our terminology is split into, well, it says two, but then with a bit of fun and games as well. So let's say we have y equals something to do with an x. Okay, what we normally have, y equals x squared minus 3x plus 4. We have y is our dependent, x is our independent variable. If we're going to differentiate this, then we end up with dy by dx. This is our gradient function. Okay. If we then second differentiation, so we get our second derivative, d2y by dx squared equals. Remember, we're covering here the entirety of differentiation in like a revision summary. Okay, so if we're using y equals terminology, then our notation is dy by dx, second derivative is d2y by dx squared. If we are using fx notation, fx equals something to do with an x. Okay, so in this case, we only have one variable. So we can't imagine a new variable and say dy by dx, well, who says it's y? Okay, we're only working in terms of one variable, so our notation then has to change. If you're working in fx notation, your first derivative, your gradient function, is f dash x. And your second derivative is f double dash x. Okay, so we always maintain that notation that we got from the very beginning. Where does the fun and games come in? Fun and games comes in, well, who says we need y and x? Okay, what if we're doing area is 2 times the width? Well, area would be width squared, but anyway. All right, so let's say we have a relationship between variable a and variable b. So remember, a is our dependent, b is our independent. They have the same set pattern as y and x from our first example. So our notation here becomes dA by dB. There's our first derivative. And d2a by dB squared. That's then our second derivative. So your notation is critical. If you say fx equals 2x squared, dy by dx equals 4x, you're wrong. Okay? You don't have a dy by dx in that case. You had fx to start with. So it's really important that you maintain that notation through the question. And it's really important that you use y equals when you talk about the function. Dy by dx for the gradient function. Okay? The other thing you're going to do, which you can't really see because I don't have lined paper, is each time you change type of function, you're going to skip a line because it's a whole different type of function, so it is separated. So notation is really critical, and it's something I've found when marking assignments is that this is one of the areas where students stuff up very quickly, very fast, lose their marks. So it's not about that they didn't know how to differentiate. It's about they didn't pay attention to the notation. So make sure you pay attention to your notation. It's something straightforward and it's simple, but don't overlook it because it's a critical part of actually how you communicate your answer to your examiner, to somebody who's reading your mark, reading your work. Okay, right, so there's our notation. How do we actually differentiate? We've got 3 basic patterns we're going to talk about. Okay, and nobody's squealing, but somebody should be. If they're all sitting here together, they should all have different function names. Okay, function notations that you learned in functions still applies to differentiation. So if we're going to differentiate the first one, fx equals kx to the n, we skip a line, f dash x equals k n x to the n minus 1. G dash x is a k n ax plus b to the n minus 1. Remember to bring that a out. He often gets neglected. Okay, h dash x is more fun. This is not linear. See, ax plus b, that's x1 over 1. It's a linear core. This is not a linear core, so h dash x is going to be our chain rule. So we would have to say, let us say, let y equal k ax to the m plus b to the n. Then we would say, let u equal ax to the m plus b. Because remember, we always take our core out. That's our u. Then we would be able to differentiate different pieces, have all sorts of fun and games, and end up with dy by dx equals du by dx times dy by du. Bring everything back together. So when we're talking about just working with straightforward functions, okay, we're not touching so much on applied differentiation now here, with more fun games that you can have with that when it comes to the chain rule. Okay, but when we're talking about just straightforward differentiation, these are the three situations that we're talking about. Simple solitary term, linear ax plus b, or non-linear, all sorts of fun and games leading to the chain rule. Remember, if you've got multiple terms, if you've got k, if you have kx to the n minus j ax plus b to the n plus tx to the n, okay, doesn't matter. Remember, when you differentiate even if you have a plus 6. You differentiate each term, okay, and then you carry them on. And it doesn't matter how many terms you have, you can do each one separately. The important thing to remember and to bear in mind is your algebraic form versus your calculus form. So an algebraic form would be something like 3 over x squared, whereas calculus format for this would be 3x to the minus 2. Because we always want to have it in that same format that we've got at the top here for f, g, and h in order to make our differentiation easier. So always bear in mind that if you've got it in algebraic form, this is what you use to solve equations. Calculus form, this is what you're going to use for differentiation. And when you get to it, integration as well. So before you go and differentiate, then you want to check, have I got into calculus form, reformat if needed, and then you can go and you can just apply your standard results and work down. Always simplifying your terms for your final answer. That's also another important one. Let's put that one here in bright pink. In some memos, they will give you full marks for just doing it and doing the method. In other memos, they only give you full marks if you have simplified your terms. So why play with sort of risk with your marks? You don't want to play risk with things like marks. You want to always ensure that no matter what the memo is, you're going to get those full marks. So be neat and tidy, simplify your terms, give yourself a final answer each time you differentiate. Right, so now we know how to differentiate. We know the concept behind it. What are we actually going to do with this? Where does this sort of come up in our questions and in our exams? Let us make a list. First thing, remember how we said that the gradient of a curve depends on the shape of the curve and the value of the independent variable. So we differentiate, we get ourselves this beautiful gradient function. First thing we need to be able to do is find the gradient at a particular point on the curve. So one thing we can do is find the gradient at a point. We're going to use the independent variable in order to get this value. So for example, we would have f dash of 2 equals, because f dash x would be our gradient function. F dash 2 would be the value of f dash x at x equals 2. If you're using dy by dx notation, you can do an at x equals 2 dy by dx equals, and you would substitute that 2 in. Okay, so same thing. If you have f dash 2, there's no more x's on the right-hand side. It's 2's on the right-hand side. Always make sure that you keep in that notation. As soon as you say, I'm going to substitute, do that substitution. Okay, what else do we do? We could work this backwards. We could say, given the gradient is 5, where does that happen? Okay, so you could find a point or multiples with a particular value. So in this case, we say, well, the gradient equals 5. If it was a straight line, you could say m equals 5. Finished. Over. Okay? If it's a curve, there is no such thing as m. There is no one value. But you know that the gradient of the curve is f dash x. Okay, and that equals, let's say, 5. Why not? Okay, so gradient equals 5. Then we go back to what we learned in functions, and we say, well, f dash x is the name of our function, of our gradient function in particular now. So f dash x we can replace with the algebraic statement that represents f dash x. And then we can solve for x, and we can end up then with the value of our independent variable. So we're just doing the first one back to front. Okay, so you would also have, if you're using dy by dx, you would have dy by dx equals 5, for example. And then dy by dx is the name of your gradient function. So you would just substitute in then the algebraic expression that represents your gradient and solve for x. Next thing we do is we work with tangents. Okay, tangents are wonderful when it comes to curve because the gradient of the tangent, remember, tangents don't cross a curve where they touch. So a tangent to a curve at x equals 2 is going to kiss that curve for a slight moment of a fraction of a second, okay, before it leaves again. So in that slight moment of a fraction of a second, the gradient of the curve and the gradient of the tangent are equal. Brilliant. Now we can link straight lines and curves and gradients and have all sorts of fun. Okay, so we can work with tangents. We would say here, at x equals k, so at a particular value, remember k is a constant, so it's a number, then we would say f dash k equals mt. F dash k, so the value of our gradient at k equals the mt. M is our gradient for straight line only. T represents our tangent. So gradient of our curve equals gradient of our tangent. Your world expands in AS Maths because we add in normals. Okay? Your normal is perpendicular to your tangent. So at x equals k, f dash k equals mt, and we know that mt, mn equals -1 because normals and tangents are perpendicular. So please bear in mind here that we don't go from the curve to the normal, okay? We are going from the curve to the tangent, from the tangent to the normal. As always with math, if we can do it in one direction, we can do it in the complete opposite direction. So we can go from the normal to the tangent, from the tangent to the curve. Okay, so the tangent acts as your middleman in between your curve and your normal. So don't go from curve to normal or normal to curve. Always go through that tangent. Mention him on the way because he's the linkage between your curve and your normal. Okay, the other big thing here in layout, I mean, these questions can get really fun. These can be half a page, full page calculations. And there's a lot going on. You've got fx, you've got f dash x, you might have f double dash x. Okay, and you've got to keep a note of what's going on. Okay, so the last one, before we get into that point properly, we're going to talk about classification of stationary points. because this is the other thing we do with differentiation. This here, remember, is your second derivative. Okay, and it's all about whether that second derivative is positive or negative. It's not about the value of the second derivative, it's about the sign of the second derivative. Okay, if your second derivative is negative, then you have a maximum. If your second derivative is positive, then you have a minimum. Oopsie. So when it comes to classifying stationary points, yes, we learn how to do it with a gradient pattern, but then we very quickly learn that using the second derivative is much faster, much more efficient, and much less prone to error. So we sort of say, okay, all right, I've learned how to do it with a gradient pattern. If you continue to A-level maths, then you will be doing it by gradient pattern, because in A-level maths you come across functions where you can't do it using the second derivative. So gradient pattern is a really powerful technique, but the thing with really powerful techniques in maths is that they often take a little bit longer. So certainly at AS maths, your second derivative is the one you really want. That is going to give you straightforward, simple, direct answer for your classification of your stationary point. So these are all the things we do. We often combine many of these within one question. So the format note to make on this one, remember you're always simplifying your terms from the last one. You are going to be using subheadings. In your answer to clarify what's going on. Okay, it makes it easier for you to track. I'm doing this, to do this, to do that. Makes it easier for you to check at the end of your exam. I did this, I did this, I did that. And then, of course, at the end of the day, it makes it easier for your examiner to follow. They did this, they did that, they did this. And so it's beneficial to everyone. If you have an organized sort of frame of mind when you enter this question, then you have a far more organized answer that you're generating out of your working. And that is, remember that your communication of your answers is critical when it comes to AS Maths. We're not just looking, can you add? Okay, the idea is, can you understand the question? Can you figure out what you need to do? And can you communicate what you're doing clearly so that it can be followed by somebody else? So we're working on a communication skill here as well. And these big differentiation questions is where it really starts to kick in, as to make sure that you're keeping track of what you're doing. Right, so that is what we use differentiation for. Okay, the other sort of last element of this is the applied differentiation. When we're talking about applied differentiation, we're talking about a farmer has so much land and he wants to make somewhere for his very strange looking animal with a tail to stand and eat, and how big can he make the field, or how does he minimize this? Or we are talking about rates of change of growth, and we combining different variables. If we have area and we have radius and we have time. Okay, remember when we talked about very beginning, it was dy by dx, it was y equals to do with x, it was a equals to do with b, it was the a by the b, it was only ever two variables. Okay, so here we have, let's call them real life situations. And here we have three variable situations. Okay, so your real life situations, I mean, there's nothing new, there's no new mathematical technique that we're going to add into this. What we might do that might scare a few of you is to bring back some geometry. Remember at IGCSE, you did a whole lot of geometry, areas, volumes, surface areas. That can come back now. Okay, remember, AS Maths assumes full knowledge of the extended IGCSE Math syllabus. So everything is open to presumed knowledge. What often comes in is your basics. It's your circles, your squares, if you can spell squares, it's rectangles. If they generally give you something like a cone or a sphere, they actually give you formulas for it. Cylinders they like to bring in. Okay, so keep this in mind. If you're a person who struggled with geometry, then maybe it's worth going back and just making yourself a nice little study summary of all the formulas for area, for surface area, for 3D shapes, for volume. All those things that you learned way back in the day, because they come in useful here. Because often in a real life situation, the first thing you're going to have to do is prove a relationship between area and length of the width of the field. Okay, so it's something that you want to be able to do that, show that question, so that you can then do the differentiation question afterwards. Makes you feel a lot happier and smoother going in. When it comes to the 3 variable applied differentiation, this is where we are using our chain rule to link. So here we would have things like dA by dr, we would have dr by dt, and we would have dA by dt, and we'd have to think, okay, where does my chain fit in? So remember, it's always the ones that look like they cancel that belong together. So in here, if we look, we've got t's on the bottom, a's on the top, r is on both. So this one would give us dA by dt equals dA by dr times dr by dt. And then we would get all our different rates, and we'd look at when we're looking at it, and values of independent variables, and we'd chuck everything in. So again, okay, applied differentiation is nothing brand new in terms of technique. But what it do is it's taking that plain technique and saying, okay, now in a situation, do you know what you need to do? So if my question talks about increasing or decreasing or maximizing or minimizing, then this is what I'm going to do. And that makes me realize there is one other thing that we missed off our list in the previous one. Okay, so go back to your notes and add in increasing and decreasing functions. We did, I think it was 5 things. So if it was 5, call it 6. If it was 6, call it 7. Increasing, decreasing functions. So this is where we're looking for an increasing function is going to have gradient always positive. Decreasing function going to have gradient always negative. Okay, so that is another thing that we do with differentiation that's quite fun, where we look at classification of our function rather than just classification of our stationary point. Okay, so as with everything, understand the question, go slowly, make sure you read through it properly, get all the information out of it, and then go ahead and solve it. But structure your answer so that it's easy to follow and easy for you to work through. We are fast running out of time now, so we shall continue next week with some past paper questions, looking at how we actually translate all of these different techniques into actual questions and answers.